Section 6.2, definite integrals. So what we have in the figure on our first slide is just some function f of x between x equals a and x equals b. And we are going to talk about breaking this into subintervals and forming rectangles and finding the area of these rectangles to approximate the area under the curve. So we talked in class about parsing through this notation to understand what it is they're trying to tell us. So here is our function f of x, and you can see that we have broken it up into subintervals, calling a x sub 0, and over here our end of the partition b, x sub n. So we can break it up into any number of rectangles, and the rectangles can be above or below the x-axis. And the subintervals can be the same size, or we could use subintervals that have different widths. So number 1 just tells us that we're dealing with some section of f of x on the interval from a to b. Number 2 then says we break it up into n subintervals, where we can find the width of each of those intervals by doing the right side, x sub k, minus the left side, x sub k minus 1, to find the width of the interval. And then within each subinterval, we choose some x value, which we'll call c sub k, for whatever case interval we're talking about. So here you see c sub 1, because that is the x value we chose in interval 1. Here is c sub 2, because that is the x value we chose in the second subinterval, and so on. So we talked about in class doing a left rectangle approximation method, a right rectangle approximation method, and a midpoint rectangle approximation method. Well, we could choose anywhere we want for this c value. It could be the left point of the interval, it could be the right point of the subinterval, it could be the middle, it could be anywhere in there, and then we plug that x value into our function to get the height of our rectangle. And that's what number 4 is telling us. That on each subinterval we stand a vertical rectangle that reaches from the x-axis to the top of the curve, to touch the curve. The rectangles could lie either above or below the x-axis. So at any time, if you are asked to calculate a Riemann sum, that is exactly what we've been doing, breaking the area under the curve into some number of rectangles and finding the area of those rectangles and adding them up. So this s sub n is the sum from k equals 1 to n. So if we had 12 subintervals, then our n would be 12. And this is f of c sub k times delta x sub k, which just means we multiply the height of the rectangle in that subinterval times the width of that rectangle in the subinterval. And then we add up all of the areas of the rectangles. So then, if we come over to the definition of the definite integral as a limit of Riemann sums, here is exactly what we just developed. The sum of the heights times the widths for all of the rectangles. And then if we let this p with the double lines around it, which is called the norm of the partition, and that is the longest subinterval length in the partition, if we let that length approach 0, well, that means that if the longest subinterval approaches 0, maybe it's that one, then that ensures that every other subinterval in the partition would also approach 0. So basically, this is saying that we take the limit of the sum of the areas of the rectangles as the number of rectangles approaches infinity, as we make really, really tiny rectangles and add them all up. And this is the definition of a definite integral. So what I want you to think of when you see the definite integral, or the terms, the definite integral, I want you to think area under the curve. Put it over here. And when we say area under the curve, we're talking about the area between the curve and the x-axis. All right. So now just working with the terminology. The definite integral symbol is the integral symbol with a lower limit of integration and an upper limit of integration. So if you see an integral sign that has a number on the bottom and a number on the top, that is a definite integral, and we are doing area under the curve, which is the area between the curve and the x-axis. One thing I wanted to note, and we noted in class, is that basically a definite integral in calculus is a summer. It sums a great number of things, an infinite number of things, and it is summing the height of a rectangle, f of x, times the width of the rectangle, which if we have an infinite number of very, very tiny rectangles, then the width of each one would be dx. And as we move forward with working with integrals, I want you to make a note that when we perform the mathematics necessary to calculate an integral, that we have to do no work on dx. dx is there to tell us what variable we are taking the integral with respect to. So we'll keep that in mind as we move forward. All right, so one theorem that we should keep in mind when we are finding definite integrals is that all continuous functions are integrable, meaning we can take the definite integral of all continuous functions. So down here we have an example of a discontinuous function with a large area where the function is not defined. So we would have no definite integral from a to b on this function. Over here where we have this vertical asymptote, if I draw it in, coming down here, it is possible with what is called an improper integral to find an area under this curve, but it also could be that it would not be possible. We do not have the skills right now to determine if the area under that curve is possible for us to figure out. So it could have a definite integral from a to b, and it also could not. We'll figure that out a little bit later. But what this theorem is stating is if the function is continuous from a to b, then the definite integral exists. All right, and then just notation. This notation right here, the definite integral from a to b of f of x dx, finds the area under the curve, and if f of x is non-negative, then this represents the area under the curve. Now, if f of x is non-positive, or f of x is below the x-axis, then the area under the curve is the negative of the definite integral from a to b of f of x dx. So what we're saying here is when we deal with definite integrals, we have signed areas, positive or negative. And let's take a look now to see if we can clarify when they are positive and when they are negative. So I have a function sketched right here, and I've labeled the x-intercepts. This one is A, this one is B, this one is C, and this one is D. So when we are figuring out if the area is a positive or a negative, let's take into account that we are basically summing up a bunch of rectangles. So if I sketch in this, I'm coloring this little area to be one rectangle, one representative rectangle. Kind of fat, but there it is. And what you want to look at is if our motion in the x, so if we're going from A to B, here is my A, here is my B, my motion is to the right, which is a positive x, and the rectangle is above the x-axis, which would be like this one right here. That's a representative rectangle. So to find the area of that rectangle, we're moving from A to B, so that's in the positive x direction, and the y value, or the function, is above the x-axis, so that is a positive function value. So we basically have a positive times a positive, if we were doing base times height for this rectangle, giving us positive area. Okay, so if we look over here, the integral from a to b of f of x dx is a positive because the our x is moving in the positive direction, and the function value is positive, so positive times a positive is positive. If we look at the integral from b to c, well, we again are moving in the positive x direction. We're moving to the right, but this time our rectangle is below the x-axis, so that would be considered a negative. Positive times a negative is a negative. Let's look at the integral from c to d. Again, moving in the positive x direction makes for a positive width, and the function value is above the x-axis. Again, we end up with a positive value for that area. So if I, oopsie. All right, and this green rectangle right here represents one of the rectangles we would be summing up from C to D. So that's showing that the function value is above the x-axis. If we look at the integral, right there, here we go, the integral from D to B. So looking back at our picture over here, now we're going from D back to B here. I've labeled the area under the curve from D to C, I've labeled the value of that area, we'll call it P, and the value of this area here we would call R. So we could break this integral up into two parts. The integral from D to C of f of x dx, which would go from here to here, and then add to that the integral from C to B of f of x dx, which would go from here to here. So now I'm going in the negative x direction from D to C. So this area P would be a negative value because it's a negative x times a positive y. So the integral from D to C of f of x dx would be negative P. And then the integral from C to B of f of x dx, well, my movement in the x is left, so that is negative. And the rectangle is below, or the function value is below the x-axis, so that is also negative. So the sign for the definite integral from C to B of f of x dx would be positive. So the integral from D to B of f of x dx would be negative P plus R. And that's all we need for that one. All right. We also took time in class to go through this investigation, in which we have the definite integral from 0 to pi of sine x dx is equal to 2. And we are told that that is true. We will revisit it later, but we're told that that is the value of that integral. And they have a picture of that region over here, this shaded region over here. And the area under the curve there is 2. Now they want us to use what we know about the sine function and what we know about signed areas using definite integrals to calculate the values of the definite integrals on 1 through 10. So number 1 is the definite integral from pi to 2 pi of sine x dx. Well, the integral from pi to 2 pi. Alright, what I did is I enlarged the sine curve, and so what we have here is 0 to pi is right here. So if this function continued from pi to 2 pi, it looks something like, without my shaky hand, so it would be the same area as our original area, but it would be below the x-axis. We would be moving in the positive x, and the y would be below the axis, so it would be negative, and it would be negative of the value that they gave us for our original definite integral. So this would be negative 2. Number 2 is the integral from 0 to 2 pi of sine x dx. So let's go back down and look at our graph. So here is 0, and here is 2 pi. This value is 2, and this value is negative 2. So that integral would be equal to 0. 0 to pi halves, back down to the graph. Well, pi halves would be right here, which is half of our original function. So the value of that integral would be 1. All right, now this one is interesting. The integral from 0 to pi of 2 plus sine x dx. So they're shifting the sine x function up 2. Give me a second to draw a sketch. Okay. So here is the part of the sine function that we're interested in, from 0 to pi, and we have shifted the sine function up 2. So this region right here is that same region we've been working with from the beginning, so that is 2. But now we also have this rectangle that has formed in the area underneath the function that was shifted up. So our area is going to be 2 plus the area in this region. And to get that area, this is pi, and we have moved up 2. So the area of the blue rectangle would be 2 pi. So the total area for this definite integral number 4 would be 2 plus 2 pi. All right, number 5 is the integral from 0 to pi of 2 sine x. Well, that changes the amplitude of our function, and just like with derivatives, when we have a constant out in front here, we can move it out in front of the entire integral. So this is 2 times the integral from 0 to pi of sine x dx. And that would be equal to 4. All right, now let's look at number 6. If we think about this, in number 6 we have the integral from 2 to pi plus 2 of sine of x minus 2. Well, sine of x minus 2 shifts the sine curve to the right 2 units. So the original point is here at the origin, and that moves over 2 units to here. And this point right here that was at pi moves over 2 units, so that is now at pi plus 2. And so we're looking at that function, which again looks like the same area that we've been dealing with from the beginning. And notice now that our lower integration limit is 2, which is right here, and our upper integration limit is pi plus 2, which is right here. So this is just a shifted version of our original integral. So this will be equal to 2. All right, now number 7 says the integral from negative pi to pi of sine u du. Don't be thrown off because this is a different variable, u. We can use whatever variable we want. We'll be doing the same process. So now we're going from negative pi, which is over here, to pi, which is here. And we'll have a negative 2 area here, plus an area of 2. So this will come out to be 0. All right, number 8, definite integral from 0 to 2 pi of sine of x over 2 dx. I have just gotten a visual for this one. It's a little tidier than my drawings. So, for number 8, sine of x over 2 actually makes the period stretch by a factor of 2. So it would be between 0 and 4 pi versus 0 and 2 pi for sine of x. So we are looking at still one arch of the sine curve, but it takes 2 pi to get that one arch in. So this is the graph that we're talking about. And we're talking about the area under the curve of this arch from 0 to 2 pi. So it is our same area doubled because we're still equally as high, but we are twice as long. So the area would be doubled. And so this area would equal 4. All right, and our last one is cosine x from 0 to pi. And if I used just that first graph again, okay, so cosine starts here. At pi halves, it is at 0. And at pi, it is down at -1, like this. So it looks something, again without my shaky hand, something like that. And if we're doing the integral from 0 to pi, we have half of our original arch, so the area from 0 to pi halves would be 1. And the area from pi halves to pi would be -1. So the definite integral from 0 to pi would be 0 for cosine of x. Okay, and finally, suppose k is any positive number. Make a conjecture about the integral from negative to k of sine x dx. Well, we've done a few of these already. And if we go from any negative value to positive value, let's say negative pi halves to pi halves on sine of x, this one would be -1, and this one would be +1. Adding the two together, we get 0. The same would happen if we went from negative pi to pi or negative 2 pi to positive 2 pi. So the conjecture would be that this integral, the definite integral, would be equal to 0. And it's based on the fact that this is an odd function with symmetry about the origin. Okay. Now, we talked about how to find the definite integral using our calculator. so let me fill that in here. All right, so to do a definite integral on our calculator, we will use the fnint function. And the way we get that is with math 9 on our TI-83 calculators and 84s. So we're doing math 9, which will bring up fnint. What I have here is y1, so my suggestion is that you put the integrand into your y1, just so you don't have to keep typing that same function over and over again. So we have y1, comma x, that means with respect to the variable x. Then we have another comma from -1, that's the lower limit of integration, to 2, the upper limit of integration. And that's all you would need. You would hit enter and it would be able to calculate your definite integral. And for the TI-84 pluses, it looks a little bit more like this. And you just fill in the boxes. So you would put a -1 here, you would put a 2 here, you would put a y1 here, and an x for the dx. And hit enter after that. Okay? All right. There are some cases where we can still find the area under a curve even if the curve is discontinuous. And one case where this will happen is if we have a bounded function, so we're on some interval like this one from -2 to 2, and within that bounded function there is a finite number of points of discontinuity. So in this case, the function is absolute value of x over x, which has 1 point of discontinuity, a finite number of points of discontinuity, on the interval from -1 to 2. And in this case, it would still be integrable. We could still take the definite integral, which is the area under the curve, because if you look, we certainly could find the area from -1 to 0, and the area from 0 to 2, being two rectangles shown in black here on the graph. So there are times when a function is not continuous and we can still take the integral, the definite integral, and then there are other times where we could not. And we'll look at more and more examples of each as we progress forward. All right. The last thing I want to talk about is if we have a constant function. So if you see on this one we have the definite integral from a to b of c dx. Well, c is just some constant, and if we were to graph a constant, it's just a horizontal line. So if I wanted to find the area under the curve of c from a to b, well, the width of the rectangle that is formed as the area under the curve would be b minus a. And the height of that rectangle that is formed would be c. So the area under the curve would just be c times b minus a. So if we had something like the integral from 0 to 5 of 25 dx, that would be as if our c here was 25, our a was 0, and our b was 5. So the area under that curve would just be the b minus a, 5 minus 0, times the function value, which is 25, giving us 125. Okay, and then if you look down here, same idea, but in this case our constant is negative. So if our c is negative, then we would have b minus a still for the width, times that function value, which in this case would be negative c. A good example is if we had the integral of negative 25 dx from, let's say, 1 to 4. Let's do that. And here we would get the width, which would be 4 minus 1, or 3. Times that constant, which is negative 25. And we would get negative 75. So right now, every time you see this definite integral symbol, you just have to think area under the curve. So maybe you graph the curve and then use geometry to find the area. We have not talked about a mathematical process to be used when we see this. We are just considering it as the area under the curve and calculating those areas. So that should do it for 6-2.